Hello, Gretan. How are you today? Hope you're doing fine. So, this video is gonna be finally the last one for our chapter 5, okay? We are gonna be talking here about electromagnetism, and this is the part 2 about magnetism. So, if you didn't watch the previous one, go back and watch that first, okay? So, let's go. What's electromagnetism? Electromagnetism is a science that describes all the phenomena resulting from the interaction between electricity and magnetism. Okay, so it's a relationship between electricity and magnetism, both of them together. They are connected like everywhere. And in this lecture, I'm going to discuss about the magnetization by electricity that consists of when electric current generates a magnetic field. So when I use electric current to create a magnetic field, I can do that just using dynamic electricity because I need the movement, okay? So this is not possible with static electricity. And the other is charging by magnetism. So this is the opposite. I'm creating electric current from a magnetic field, okay? And this one we call electromagnetic induction. So we have two kinds of electromagnetism. Magnetization by electricity is when I create a magnetic field from an electric current, and charging by magnetism when I create electric current from a magnetic field. Okay, so we're gonna be talking about each of them now. First, the magnetization by electricity. So we generate magnetic field. So we create magnetic field using electricity. The electrical charge must be in motion. That's why we are talking about dynamic electricity and not static, because the electrical charge must be in motion. Here is an example, an experiment actually. When my current is disconnected, as you can see here, all my compass points north. Okay, so all my compass are point north because that's their natural behavior. They always point to the north of the earth. But if I create a current, electric current here, if I connect, see what happens to the compass? They all moved. And how they moved? They moved following the directions of the magnetic field generated by the electric current. So when I create electric current here, I create a magnetic field here. So all the compass will point for this magnetic field, okay? So this shows that a magnetic field can be created from electricity. So who discovered that was Hans Christian Ørsted in 1819. He notes that the needle of a compass will deflect when it comes close to a live wire. So here is like his easy experiment. When the switch is open, it means I don't have a current here. My compass points north. So I have no electric current and my compass points north. But when I close the switch, I create an electric circuit here. My compass change the direction. And from where? Here in the wire around it, there is an electric current. So I'm gonna so around it, there is an electric current, magnetic field, sorry. There is a magnetic field here around the electric current. So the compass will point to this magnetic field, okay? So when I have an electric current, my compass point to the magnetic field created by this electricity, okay? I'm gonna post a video with this experimental explanation for you, okay, as well, to be more clear. So the magnetic field lines form circles. So the magnetic field lines form circles around the wire, and that direction depends on the current direction. How do I know the direction? There is a rule that we call right-hand rule that we can use to determine the direction, okay? So for example, if you have a wire here and you hold with your right hands, your thumb will point the direction of the conventional current. So how is the conventional current? Remember, it's from positive to negative. Okay, we know that the real current is not this, but we are using the conventional here. So my thumb will point the direction current, the direction of my current in electricity from positive to negative. And my fingers grasping the wire show the direction of the magnetic field. So I know that my magnetic field will go in this direction, like circle movements around the wire. Okay, so if you use the right hand rule, you can know the direction of the current, electric current, and the direction of the magnetic field. From your thumb is the current, from your fingers is the magnetic field. Now, they improve this performance by creating a solenoid. So solenoid is a straight live wire that identify the magnetic field. Okay, so I'm gonna show you here. Instead of having just one straight wire, what they do, they put all the wires in forming a loop like that. And when I do this, I intensify the magnetic field that I create. So the solenoid is used for a lot of purpose because they increase a lot the magnetic field that's created. Okay, so solenoid is a cylindrical coil of live wire disposed in loop like that. And then the magnetic field here in the center is the highest. Okay, so they improve a lot the magnetic field created. The intensity of the magnetic field is highest at the center. So in the center, we have the highest magnetic field created by the solenoid. The same way, to determine the direction of the magnetic field lines of a solenoid, we also have the right hand rule. But now I'm going to hold a little different, okay? So I'm going to hold like that. And my thumb will show the direction of my magnetic field inside the solenoid. So it's going to show the direction. So it's going to be from here to here, okay? The arrow shows the direction of the magnetic field. And my fingers will point to the conventional current. So my conventional current starts here and goes in loop and goes out here. So my fingers will show the direction of the electric current, okay? The magnetic field of a solenoid is very similar of that of a bar magnet, okay? So when I build a solenoid, they have the same characteristics of a bar magnet. Okay, so it's a very strong magnet. But there is some main differences. The first one, the solenoid can be switch on or switch off. So if you remember from the previous lecture, when I have a bar magnet, it's a strong magnet. So I cannot easily change the magnetic properties of it. But for solenoid, I can, if I switch on the current intensity, I have the magnetic field. If I switch off, I don't have. So I can control the magnetic field in a solenoid. In the bar magnet, I can't. The direction of the magnetic line fields can be altered by reversing the current intensity direction. So I also can reverse the direction of my magnetic field by changing the direction of my current intensity. Okay, so here in this example is going from positive to negative like that, and my magnetic field is going from right to left. So if I want to change this, I can just change the direction of my current intensity, and my magnetic field will be the opposite. So I can easily reverse. Okay, for my bar magnet, this is not possible. And also the intensity of the magnetic field can be modified. So if I want more intense, I can put more loops, for example, or increase the electric current. If I want low intense, I can decrease the current intensity or put less loops, okay? So I can control the solenoid, I can control much better than the bar magnet. That's why it's so used in a lot of applications. So the characteristics of the solenoid is explain why they are widely used in technological applications. So here there is a basic solenoid design, as you can see. This is made of a ferromagnetic substance. So remember, ferromagnetic substance is a substance that contains nickel, iron, or copper. And this substance is inserted inside the solenoid. So here is the metal inside, the ferromagnet inside, so this blue part, creating a core, okay, and like a nucleus. The magnetic field will come from the electric current of the solenoid and the magnetization of the core, okay. So the electric field, if I do like that, I have a magnetic wire as well that creates a current intensity, and this will be intensified by the magnet that I have inside. So the magnetic field will be created by the electric current of the solenoid itself and also by the magnetization of the core, because the core is a ferromagnetic substance. This results in a very powerful magnet, which can be turned on and turned off. So we have some bar magnets that are very powerful, but the disadvantage is that they cannot be turned on or turned off. In my solenoid, like that, is also very powerful, and it can be turned on and turned off. That's the huge advantage. So here an example. If I have a switch off solenoid, for example, there is some magnetization here that is attracting this, let's say iron, I don't know what's this substance, but there is some magnetization and it's attracting, okay? But see what happens when I switch on. See, when I switch on, I just put electricity here. So when I switch on, this becomes a much more powerful. So here attract much more. See, it's much more powerful because I increased the intensity of the magnetization by putting electricity. That's why the solenoid electromagnets are so powerful. Because they are so powerful, they are widely used to transform electrical energy into mechanical energy. Okay, so electrical magnets are widely used in a lot of applications. The power of an electromagnet can be increased in three ways. So I can increase this power by doing three things. First, I can increase the intensity of the current intensity, the electric current that I have flowing there. I can add more loops over there, and I can use a core with a lower magnetic intensity. What remanescence? Why lower? Because remember, lower magnetic remanescence, they are more flexible. They lose or they gain magnetic field more easily. If I use a higher magnetic field remanescence, it means it will be a permanent magnet, and that's not what I want because I want to have more control. Okay, so if I use a lower magnetic remanescence, it means this object will lose or will gain magnetic field more easily, so I can easily control, okay, by putting or by removing the electric current. For example, if I put a higher magnetic remanescence, my material will be permanent magnet, and that's not what I want. Okay, because I have to have control. Okay, how do I charge now? By magnetism. Now I'm gonna do the opposite. Okay, I'm gonna create electricity by using magnetism. This was made by Michael Faraday in 1831. He proved that it was possible to generate electric current from a magnetic field. Okay, so what he did to generate an electric field, a magnetic field must be in motion. Okay, so my magnetic field must be in motion. And there is two ways of doing my magnetic field in motion. Okay, by a charge or a conductor. So let's say by moving a conductor. So here I have this diagram. This is my magnetic field, okay, and this is my conductor. So my conductor is rising and my conductor is falling. So when I create this movement of rising and falling, I create electric currents, as you can see here. When I rise and move, my electrical current will be created or create an electric current here. So by moving the magnet of my magnetic field, see, the magnetic field is here, and I'm moving the conductor inside the magnetic field. This movement of the conductor is making me create electricity, because as you remember, electricity current intensity, I need movement. If I don't have the movement, I don't have electric flow. And there is another way, by moving the magnet itself. Okay, so in the first one, I move just the conductor, but I can also move just the magnet. So here I have my magnetic field, and I can rise or I can lower, falls my magnetic. When I do that, I create electric current. Okay, so by rising or falling my magnetic bar, I can also create electric current. So here we are doing the opposite. We are creating electric current from a magnetic field. I can do that by moving my conductor up and down, or by moving my magnet itself. When I do this movement, I create electric current. So electromagnetic induction consists in generate an electric current in a conductor by varying a magnetic field. So I'm changing the magnetic field. When I change that, I create an electric current. The intensity of this magnetic field and the speed in which it moves are important factors in electromagnetic induction. So I control the intensity and the speed that I want by the movement that I do with the conductor or the magnet. This is widely used to transform mechanical energy into electrical energy, so it's the opposite. This is the principle behind the most electric generators. So in a hydroelectric power plant, the water moves? The water moves the turbine, right? When it moves the turbine, what happens? So water flowing through the dams spins a turbine, causing the electromagnets. So here inside the turbine, I have electromagnets. So I'm moving my electromagnets. By moving these electromagnets, I create electric current. Okay, so now you can understand much better how an hydroelectric plant works. So how do I create electricity from magnetic field? By movement. By movement the magnets or the conductor. How this applies for hydroelectric plants? When my water falls down, it moves my turbine. My turbine has a lot of electromagnets. These electromagnets, when they move, they create electric current. And then this electric current is collected through the wires and is is transferred to the wires until it goes to your home. Okay, so now we can understand much better how the hydroelectric power plant works. Okay guys, so that's it. Thanks so much for watching. I'd like to thank you for all the patience and for all the collaboration during this hard time as well. Okay, I'm very proud of you. So thank you so much.